on the fate of injected CO2 and the potential for geological storage of CO2 in India by Mr. John Williams, geoscientist, British Geological Survey, UK. Mr. Williams has worked in carbon capture and storage research at the British Geological Survey since 2006. He is a geoscientist with an interest in many aspects of subsurface usage for energy storage and extraction, as well as CCS. His research includes studies on geothermal energy potential and natural gas storage in both plastic reservoirs and engineered storage caverns. We kindly request Mr. John Williams to deliver the session on the fate of injected CO2 and the potential for geological storage of CO2 in India.
Hello, thank you for the kind introduction. My talk is roughly split into two parts. To begin with, I'm going to talk a little in very basic terms about what happens to CO2 after it's injected into the subsurface, where does it go and how does it react. And additionally, I'm also going to discuss the potential for geological storage of CO2 in India. So first of all, let's take a look at India's CO2 emissions. I'm sure throughout this conference we've seen far more up-to-date figures on this. But the point I want to make on this slide is that, at least in 2004, approximately half of India's CO2 emissions were from large emission point sources that may be suitable for CO2 capture. And in 2008, the Indian government provided backing for up to 9 so-called ultra-mega power projects, these UMPPs, which would add an additional 36,000 megawatts of capacity, but would correspond to an increase in CO2 emissions of some 275 million tons a year. So, after CO2 is injected into deep subsurface reservoirs, which tend to be in the region of about 800 meters or more below the surface level, where CO2 would exist in a highly dense phase, the CO2 becomes trapped by a variety of processes. And these include structural, residual, solution, and mineral trapping processes. And the proportions, relative importance of each of these different trapping processes differ widely between different storage sites. And something that's important to note is that once injected, not all of the CO2 would then subsequently be recoverable. So a portion of the CO2 will permanently be locked within the reservoir rocks, even if we, for some reason, chose to extract it. So in structural trapping, when we consider CO2 storage, we tend to favour structural traps, such as these examples here, because when CO2 is injected into a subsurface reservoir, it tends to rise buoyantly up to the top of the reservoir, where it becomes trapped in the reservoir cap rock. From there, under buoyancy effect, it tends to rise up into the shallower structures. So we like these structural traps because when we inject CO2, we can estimate or predict where the CO2 is actually likely to end up. So in residual trapping, we need to remember here that the CO2 is stored in tiny pore spaces, either between sand grains or in naturally occurring fractures or cracks in reservoir rocks. And during CO2 migration, CO2 displaces the formation waters, which naturally occur within these rocks. So as the mobile three-phase CO2 plume moves updip throughout the reservoir, we can see that some of this brown water actually moves back into the pore space behind the plume, and this can trap a portion of the CO2 residually behind by coherent forces. So from this cartoon here, we can get the idea that the further this mobile phase of CO2 or CO2 plume migrates throughout the rock body, the more CO2 is actually going to be residually trapped left behind. So in solution trapping, we see that a portion of the CO2 can be trapped by dissolution processes. So here, the CO2 dissolves within the brine, and this brine, which is enriched with dissolved CO2, tends to be heavier than the original brine, and this causes it to sink down towards the base of the reservoir, whereas it essentially exists in a fairly immobile state. So we can see this process in a simple laboratory experiment. Here we have a tank of glass, which is filled with tiny glass beads, and we fill this tank up with water, and then we inject CO2 into the top of the tank. So here we are before injection, and then 100 seconds later, we can see that the CO2 has started to form these dissolution sinkers. And then just a few minutes later, you can see that these well-formed dissolution fronts are starting to become highly dense and to sink towards the base of the tank. So in nature, of course, this process is much more difficult to predict because of the inherent heterogeneity within CO2 reservoir rocks. And this density contrast can actually induce convection currents, which can actually act to improve this dissolution process. So finally, in mineral trapping, when the CO2 dissolves in this formation water, it can form a weak carbonic acid, which can then subsequently react with the host rock to form new carbonate minerals such as calcite. So we see in this cartoon here, we have 3 layers of CO2 floating around at the top of the reservoir within the pore space. Beneath this, we have dissolved CO2 occupying the pore space, and this is actually reacting with the individual sand grains to form these carbonate crusts. So we heard a bit about this kind of process in the last talk, and this portion of the CO2, which is reacted with these sand grains, is essentially locked up and chemically bonded to the reservoir rock itself. And the rates at which these processes will occur in nature are likely to be highly dependent on the composition of the reservoir rocks, the cap rocks, and also the composition of the fluids that reside within the pore space, as well as the chemical composition of the CO2 stream itself. So is the CO2 pure CO2, or does it contain other compounds? And so sequestration is also possible in basaltic and ultramafic rocks, and I'll come back to that later on. So what about the long-term fate of the CO2? Well, here we have a conceptual diagram, we call this the tracking diagram, and this plots time on a logarithmic scale on the x-axis. So we see from this diagram that, at least initially then, this full containment forms the primary tracking x. This is a structurally rapid tracking. And as time goes on, and more of the CO2 migrates around within the reservoir rocks, we see the residual trapping processes have more of an effect. And over much longer timescales, the solubility of mineral trapping processes may increase in significance. Now, I have to note here that this figure is highly conceptual, and you can imagine that for different storage sites where the conditions are obviously different, this diagram might look slightly different. This is the conceptual predictive diagram to show us how the CO2 will track in the long term. So let's have a quick look now at a real-world storage situation. This is an example of the Sleipner CO2 storage project in the Norwegian sector of the North Sea. And at Sleipner, some 1 million tons of CO2 has been injected every year since 1996 into the deep sandstone below the North Sea. And the CO2 interceptor has been monitored at Sleipner using this fantastic time-lapse 3D seismic reflection data. So in these upper panels here, we see a single seismic cross-section throughout the reservoir. Also, the top of the reservoir is here, and this is the base. And this is what the seismic data looks like in 1994, prior to the injection beginning. And you can see that there's not a lot going on there, but then in 2001 through to 2008, you can see that CO2 injected at this point here starts to rise up towards the top of the reservoir, and it starts to spread laterally beneath the reservoir cap rock and beneath these thin layers of inter-reservoir shale. So these lower panels here show us the evolution through in plan view. Now these kind of monitoring data are critically important if we actually want to predict long-term state of CO2, because we can use these monitoring data to calibrate our numerical simulations, which we can use to predict where the CO2 will migrate to. Now moving on to the second part of my talk. In 2008, the IEA Greenhouse Gas R&D program published a regional assessment of the potential for CO2 storage in the Indian subcontinent. Here it predicts that there is contributors to that. I'm obviously here with the geological survey. Now the aims of this study were to analyse the CO2 capture and storage potential in India, Pakistan, Bangladesh, and Sri Lanka. So we would produce a database of large emission CO2 sources and potential storage sites. And we ranked the prospective sedimentary basins in terms of the potential for CO2 storage. And storage capacity estimates were produced for repeat oil and gas fields and for coal fields, and these conform to established carbon sequestration leadership reporting methods. So the remainder of this presentation I will use to review the storage capacity of each. So storage in India, or storage potential in India, I should say, exists in the following forms. First of all, we have oil and gas fields. So this could be storage in depleted fields, or as part of integrated storage with enhanced life-long recovery programs. We also have potential in saline aquifer storage, and these are your brine-saturated sandstone and carbonate reservoirs. We also have potential in deeper mining coal seams, and this could possibly include an element of enhanced coal bed methane recovery. And finally, we have potential for mineral sequestration of basalt formations. But I'm not going to talk too much about that, because as of yet, mineral sequestration of basalt is a relatively young technology, and it hasn't yet been proven on the industrial scale. So this map here just shows us briefly the general distribution of storage potential in India. These coloured polygons, these are the major sedimentary basins in India, and you can see that many of these are located around the peripheries, around the coastal regions, around the peninsula. And then we have some older sedimentary basins, so-called mountain basins, within the interior. And it's these old basins that tend to include India's coal beds, whilst the utmost, the oil and gas fields tend to be located in some of the coastal regions and offshore. So, what about the storage potential in the oil and gas fields then? Well, as part of the report, we concluded that the total storage capacity in India's oil and gas fields, once depleted, should be somewhere between 3.8 and 4.6 gigatons of CO2. Now, this sounds like a large number, but unfortunately, many of the fields individually, so by themselves, are fairly small. So wouldn't be expected to be able to house the emissions from a single medium-sized coal-fired power station. However, the exception to this could be the Bombay High Field, which is located offshore in the Mumbai Basin, and we have a tentative estimate of the storage capacity for this field of over 600 tons. In addition, there could be some lucrative opportunities for enhanced oil recovery, particularly in the Barma and Pambay Basin. So India has a lot of coal, we all know that. And as we did in the last report, coal can be used to absorb CO2. So as the CO2 is absorbed, it can be bonded to the coal, it can actually release methane gas, which is otherwise bonded to the coal, and this can actually be produced as part of coal bed methane projects. So our estimate of the storage capacity in coals above 1,200 litres that are not likely to be mined comes out as only 345 million tonnes of CO2, which is slightly disappointing. But one of the reasons of this is that much of India's shallow coal will, of course, be mined at some point. So it's highly likely that anyone is going to utilise any coal resources by using them to store CO2. In addition, none of the individual coal fields actually have the capacity to store any more than 100 million tonnes of CO2. So we're not looking at very large storage potential in the coal beds. So what about the saline aquifers? Well, globally, saline aquifers are thought to offer a very significant global storage resource. However, because they haven't produced hydrocarbons, they tend to be relatively poorly underexplored. They haven't necessarily been drilled to the extent that oil and gas reservoirs. So this means that there's insufficient data in the public domain, which we could otherwise use to come up with some storage capacity estimates. However, for this study, we simply classified the basins as being either good, bare, or limited potential. So for those basins that are thought to have good storage potential in saline aquifers, these have proven containment. So we know that they presence of oil and gas fields prove that the reservoirs and the caprock successions are capable of storing buoyant fluids over geological timescales. So we might also expect there to be good saline aquifer and caprock quality and suitable depths over large parts of the basin. Those basins with a fair storage potential, these may have one or more potential regional reservoirs and caprocks at suitable depths. And in addition, these may contain potential structural closures which CO2 could be stored and trapped. For those basins with a limited potential, these either lack suitable reservoirs, they may lack suitable caprocks, or they may just lack any form of structural closure to define areas in which CO2 can be stored. Additionally, they may be located in structurally complex coal belts where large-scale CO2 storage is unlikely to occur, or they may face major potential conflicts of use, such as coal mining or large-scale water extraction from deep aquifers. So here we see this map again, just so that we can have a look at the distribution of the saline action storage potential. So the sedimentary basins are represented by these large polygons. The red ones are those with a good potential for aquifer storage, the yellow with fair or medium, and the green with low storage potential. So we can see that these basins contain the hydrocarbon fields tend to be located largely on the peripheries. So to summarize the storage capacity of India, the oil, gas and coal fields combined are estimated to have less than 5 gigatons of total CO2 storage capacity. And this is only enough actually to store the national emissions from India's large point emission sources for a period of 5 years. However, the CO2 storage potential in India's saline aquifers is currently unquantifiable, but is likely to be very highly significant. So with this in mind, it's perhaps critical that the sedimentary basins are investigated in more detail using deep well and seismic reflection data. From these data, we can calibrate our geological models, and then perhaps we can use these to carry out some numerical simulation of CO2 injection, which will give us a much better handle on the actual quantifiable storage capacity. So this map here, I've simply overlaid the locations of these large point emission sources. These are the small coloured points here, the legends down here, for you to read it. These large black points here, these are planned large emission sources. Remember, this study was carried out in 2008, so these emission data were probably woefully out of date by now. And these green points here, these show us the locations of the planned so-called ultra-mega power plants. So we can see that some of these are located quite randomly to these basins that are likely to have a good storage potential, whereas many of the emission sources are located within the interior, and some of these may be hundreds of kilometres from sites which are likely to have a good storage potential. So it's clear that there may be, many of these sites, some severe transportation and infrastructure issues associated with increased costs and these large transportation distances. However, I think there are still grounds for optimism because there are some very large emission sources near to some of these sedimentary basins. So the storage capacity can be examined in more detail. I'm sure that there will be very good opportunities for aquifer and oil and gas fuel storage in India. So what about sequestration of basalts? I mentioned this earlier, and the reason I mention it really is because India has a lot of basalt. I outlined the injected tracks here in red, and basalts can be used to sequester CO2 by mineral trapping. This is because of the reactions of the CO2 with the basic minerals that make up the basalt and bond the CO2 to the basalt rocks. And the good thing about basalts is that some of these reactions can actually, well, they're said to be able to occur at fairly low temperatures, so that's a positive thing. Now, the sequestration of basalts were not quantified during the IEA greenhouse gas study because the technology today has not been proven on a large scale. However, in the future, these basalts, the depth traps, may provide significant additional storage potential for India. So, in conclusion, the storage potential in India's oil and gas fields could be up to 4.6 gigatons. However, most individual fields have a fairly limited potential. Now, the storage in coal provides a capacity of only 345 million tons, as most of the shallower coal beds are, of course, likely to be mined at some stage. So we have limited potential for CO2 storage over much of the peninsula due to unsuitable geology and potential conflicts of interest such as coal and aquifers. However, the saline aquifer potential of India has not actually been quantified, but we believe it to be very significant. And those basins likely to success, the best options are those containing hydrocarbons. I listed these here, so I won't say them all out loud. We also have some options for enhanced oil recovery, particularly in the Cambay and Barmer basins. and there may be some significant additional capacity available if the concept of CO2 sequestration in flat soils can be improved at some stage in the future. So thank you very much for listening, and I'd just like to acknowledge my colleagues at DGS who helped out with the